Hello, I'm Dr. Ian McCullough from Johns Hopkins University, and this lecture is going to cover different types of interannotator agreement measures that you might run across. A key objective of this particular lecture is to just make you aware of different measures you're going to see in the literature if you're looking at interannotator agreement, and understanding the trade-offs between them, and having a little better understanding of why we're probably going to use Krippendorf's alpha for just about all interannotator agreement measures. The 7 common methods of interannotator agreement that we see: percent agreement. You'll see Bennett's S, or you'll just see S as a measure, is the common measure for that. Scott's pi. You'll see a lot of kappa measurements. There's Cohen's kappa, Fleiss's kappa. And then we have alpha. So Krippendorf's alpha is an extension of Cronbach's alpha. And Cronbach's alpha is not really a very good measure of interannotator agreement, but we'll talk about that shortly. So these are the most common ones that you'll see. You will see some people using F measure, which is incorrect and wrong. I'll explain why later. And let's begin with the easiest one. What makes a good interannotator agreement measure? And so I would submit to you that there are 5 properties when we're evaluating different measures that we want to achieve. So the first is we want to be able to assess agreement of 2 or more observers who have independently assessed content. So when there's collusion, you're not really measuring interannotator agreement. You're not really being able to say, has the task been defined well enough where 2 people can agree, right? Can independently agree. So we're looking at independent assessment of 2+ observers. Property number 2, we shouldn't have the index, right? The index of how good the annotation is should not be somehow dependent upon the number of categories or the scale points, right? Is this a rating of 1 to 5? Is this a yes/no label, right? We don't want that index to be confounded by the number of categories or scale points. We would like to have interannotator agreement be a numeric scale between 2 fixed points, and so that allows more direct comparison between data sets, between annotations. It gives us a benchmark of whether we've achieved a sufficient quality or not, or level of agreement or not. Number 4, we want to maintain the mathematical structure across different forms of data. And so, that would be nominal, ordinal, categorical data, right? Do we maintain the same mathematical structure, or can this only be used for one type of data and not all types of data? Also, the sampling behavior of how we're sampling data for labeling should be known. So those would be the 5 properties that I'd ask you to consider. We're going to probably achieve that sampling behavior should be known. We're going to know how we're going to sample for all of these. So we're really going to address the first 4 criteria as we go through different annotation methods. So the first one, percent agreement, is just simply the proportion of units with the matching description. So you can look at 2 observers and you can identify, okay, they annotated 100 items, 100 things, and 85 of them they agreed on, and 15 of them they didn't. So that would be 85% agreement. That's the kind of agreement, and it satisfies criteria 1. There's 2 or more annotators, but it can't really do 3 annotators. When you start adding 3, 4, 5 annotators, how do you do percent agreement, right? Because now you have different paired choices, and that gets complicated, and that's not really what percent agreement was designed for. So it's limited to only 2 annotators. It also fails criteria 2, which was not confounded by number of categories and scale, because if you add additional categories, well, how do you treat that? Are they balanced across categories? The number of categories and the number of items within the categories are going to now confound that percent agreement, and so it fails criteria 2. It also fails criteria 3 because 0% disagreement is very unlikely, right? There's going to be some level of agreement or disagreement, and so because you've bounded it at the first, at the bottom endpoint, 0 to 100%, right? That 0% is unlikely to ever be observed, right? It's asymptotically approaches that. Then you're going to end up with not a clear idea of what bad percent agreement is, right? It's not going to be 0, but when you get 50%, is that good? Is that bad? We don't know. We don't know what that endpoint is. And then it does satisfy criteria 4, which is maintaining the mathematical structure across data for nominal data only. So it doesn't have the same consistent mathematical structure for other types of data. So when we move to Bennett's S statistic, right, this corrects the percent agreement for the number of categories. So the Q here is the number of categories you have, and so that creates a correction there, so it'll actually allow you to kind of deal with different categories. But I would argue it still fails criteria number 2, because if there's unused categories, or the number of items in each category is not the same, there's still a bias and there's still a confounding of the metric based on that, right? So it is better than percent agreement, but I don't think it fully addresses the criteria of what we call a good inter-annotator agreement measure. Scott's pi is interesting because it kind of turns this into probabilistic, a probability, right? So what it is doing is you see here in this form, pi is the probability of agreement minus the probability of expected agreement. So what it's doing is it's saying how much better did you do than chance, right? And that's over 1 minus the probability of expected agreement, so that it scales. And you'll see this basic form in several of the other inter-annotator agreement methods. And so it's still only limited to 2 annotators, right, when we do it, but this now satisfies criteria 2. So it's not confounded by the number of categories or scale. You'll also see that it has a good numeric scale, right? It's going to be bounded. It also still satisfies criteria 4 for nominal data and 2 annotators only. But if you're dealing with 2 annotators, right, this gets us to a lot more categories that are met in a good annotation metric, right, with Scott's pi. Now we're going to switch here. Now, I don't know if you noticed this, right? When we go to Cohen's kappa, look at that kappa statistic. Probability of agreement minus probability of expected agreement over 1 minus probability of expected agreement. Let's go back. Doesn't that look the same? Probability of agreement minus probability of expected agreement over 1 minus PE, right? What's different? Well, the difference here in Cohen's kappa is the way in which we calculate the expected probability, right? Probability of expected. And so what this is doing is it's creating this hybrid index. It fails in criteria 1 because the observers are not interchangeable, right? So you have to have fixed observers, but it's not a big issue, right? You can have 2 annotators. You just have to kind of fix their position. It satisfies criteria 2, right? It's not confounded by number of categories or scale. It does fail criteria 3 because of its 0 point, where kappa is 0. And it does satisfy category 4 for nominal data and 2 annotators only. But what this is doing is it's allowing for systematic disagreement in the data, right? It is the nuance of why some people like Cohen's kappa, because it allows for a little bit more structure in the way in which people disagree. But it's very rarely used. So Fleiss's kappa takes Scott's pi, right? Not Cohen's kappa, but Scott's pi, and it extends it to many observers. And the way it does it is the nuance. There's the lines above the of P naught and P sub E, right? So this is the P naught is the mean probability of agreement, and P sub E is the mean probability of expected agreement. So what that does is it generalizes it to many observers and many categories, and so it is going to hit all criteria as long as you're dealing with nominal data. It's going to hit all criteria, and so Fleiss's kappa becomes a pretty attractive measure. Now, Cronbach's alpha, we're going backwards a little bit here. Cronbach's alpha is not a measure of inter-annotator agreement, really, right? It does measure, it's not meant to measure agreement. So just to give you an idea of what Cronbach's alpha does is, if I'm doing a survey and I want to know, hey, do you like a given product, right? I think we're doing market research, and so I can say, hey, do you like this given product? And you may have heard of a Likert scale, which is an odd point scale. So 1 to 3, good, bad, medium, or 5-point, agree, I somewhat agree, neither agree nor disagree, somewhat disagree, disagree, right? Like that would be a 5-point scale. Or you could add strongly agree and strongly disagree on the ends and get to a 7-point scale, right? Like so that's like a what we call a Likert scale. And if I ask you, do you like this product? How do I know that I've actually captured the idea of whether you really like it? Like maybe there's some sort of nuance in the way I ask the question. Maybe there's some bias in the respondent. Have I really done that well? So, and what's the distribution? What's the underlying distribution of that Likert scale, right? That 5-point scale. We don't really know, right? It's just 5 points. We don't know what the distribution is. But what Likert demonstrated is if I can ask this in several ways, right? So, do you like this product? Would you recommend this product to a friend? Would you use this product again, right? All of these 3 things are slightly different ways of asking the same question, which is, do you like the product? So if I have those different items, then what I want to know is, are they all capturing basically the same concept? And that's what I'm going to use Cronbach's alpha. So Cronbach's alpha is going to say, are these 3 or 5 or however many ways I've asked the question, are they internally consistent? Do they tend to measure the same thing? And in that, we're looking to get a Cronbach's alpha range of somewhere between usually 0.7 to 0.9 as a rule of thumb. Because if it's 1 and all of them ask the exact same thing, well, then we've wasted a bunch of people's time, right? Because those questions are exactly the same. So we want to see a little bit of a variance in them so that we know that people are thinking, people are engaging with the question, but we want to see that they're not totally in disagreement or we haven't adequately addressed the question. So if we have a Cronbach's alpha on those items that has an agreement, rate between 0.7 to 0.9, and we can say that's internally consistent, then the trick is if we sum the items together or we average them, right, then we know that the measure, the composite measure is normally distributed. And that's powerful because now and only now can we do statistical inference to be able to compare, okay, here's one group, here's another group. Let me look at their index scores, right, to see are they statistically different, right? Or, if we look at different groups, or we can, we can have a baseline and say, okay, we've done this ad or we've done this intervention. Have we seen a change, right? We can now do statistical comparison. But in order to do the statistical comparison, you have to have an odd point scale, number 1. You have to be able to have multiple items that address the same question in some way. You have to have a Cronbach's alpha score that's probably between 0.7 and 0.9. And then, I guess technically 0.7 or higher. Then you can do a summation or a mean to create an index. And we would say that is now a validated index. And you can do statistical inference. So it's not really an inter-annotator agreement method, but I've seen it used quite commonly. So if I was going to use it, I would probably use Fleiss's kappa before I use Cronbach's alpha. We're now going to go to probably the premier measure, which is Krippendorff's alpha. And so this is the standard reliability statistic for content analysis and if you're assessing inter-annotator agreement. You'll see a little bit of similarity there in that 1 minus the observed disagreements between annotators divided by expected disagreements by chance. So that's very similar to the other inter-annotator agreement measures. And so here's some nuance in the way we calculate observed disagreements and expected disagreements. So let's say that there's 2 different annotators being represented, X and X prime. These are annotation labeling options for 2 different annotators. And the O, X prime, is the observed pairing between annotators. So you see, here's an item that 2 annotators paired and observed. And then that delta X prime is a difference function, which is 0 when they agree, and it's a 1 when they disagree. And so what that's doing is it's going through the document, and it's adding up all of the times that they disagreed, right? all of the items where you had 2 or more annotators, right? And they disagreed. Now, if there's 3 annotators doing it, it's going to compare annotator A to B, A to C, and B to C. So you get 3 observations for potential, that could be potentially disagreements from those pairings, right? So it's looking at all the times that any pair disagreed on something. And then below, right, you'll see that that is looking at NX and NX prime are the observed annotation labels or class. So these are all the different items or pairs that you have, that could be shared annotators. And then N is the number of pairs between the annotators total. And so what that does is it gives you an idea of what the expected disagreement should be. So the advantage of Crippendorf's alpha is it satisfies all the criteria, and it adds this other one, which is it can handle missing data, because if it's missing data, if there is perhaps some data that's missing, whether it's a pairing for the annotation, or whether it is something in the data itself, right? Then it's just not tallied, and so it doesn't penalize it, right? It's not included. Also, if there's an inconsistent number of annotators per document, so let's say one document has 2 annotators, another one has 4 or 5, right? That doesn't penalize or make it incomplete. Like a lot of these other ones would require 2 or the same number of annotators per document. This can have inconsistent number of annotators per document, and you can still measure inter-annotator agreement. Now, it could be that those documents that had more annotators, there could be something specific about that particular document or the number of items included in it that might introduce some level of bias. But generally, if we're assuming a random sample of documents and classes and items, then Crippendorf's alpha handles that. So I want to revisit this note on F-measure. F-measure is used in machine learning to measure the precision and recall of classifiers, right? It takes a harmonic mean between the precision and the recall to create a composite performance measure of a machine learning classifier. We talked a little bit about, you might want to bias a little bit more towards precision than recall at the pilot phase, because you'll get more data in time, which will boost your recall. But if you don't address precision early, you're incurring technical debt. But I just want to make the point that F-measure is not a measure of inter-annotator agreement. And when you see people talking about the F-measure of an annotation effort, it is a pretty clear indicator that they do not understand inter-annotator agreement, they don't understand the concept, and they don't realize its importance. And that is going to plague the ability for you to create any kind of machine learning solution at scale with any reasonable performance, right? So you got to get the data right. If you don't get the data right, then you're going to have issues in performance later. I'm just going to revisit this issue again. We talked a little bit about good annotation on the left, bad annotation on the right. Notice that that's Crippendorf's alpha. You'll see that equation is the same. What we're doing is we're using it, instead of measuring items of agreement or disagreement on a item of text, we're measuring it on the pixels in the annotation. And there's a lot you can do with how you treat that. And these are underexplored research questions, right? So you could even consider doing this if you wanted to for your paper. But the questions would be, do you treat every pixel? Do you treat every 10th pixel? Because you don't need to have so many pixels where, if you're thinking about an object, right? If you look at these 2 trucks, well, the bulk of this even sloppily drawn bounding box, right? The bulk of it is still the car. So perhaps you want to weight the inside of the image as like everybody gets that. So I don't really want to weight that. I really am only treating the edges, right? Like, how do you treat the definition of what is a disagreement in computer vision annotation, and does that change the impact, your thoughts on how you would assess inter-annotator agreement in something like this? Whereas I would argue that it's more difficult to measure agreement and disagreement and in computer vision than it is in natural language processing, where words are discrete, they're very clear, you either got it or you didn't get it. There's even some nuance there, but we don't need to go into that detail. And again, with our experiment, when we had 4 annotators and we dropped the most inconsistent annotator, right, you can see that the precision ended up, boosting. The recall was degraded, but the F1 score is appropriate. And so F1 score does not really give you insight into that trade-off, and precision is much more the focus of inter-annotator agreement than recall is anyway. So again, you're taking, there's just a lot you're adding with F measure. You're averaging what's the threshold you're using for that precision recall trade-off. You're adding in recall, which has nothing to do with labeling consistency. So you're really muddying the water on inter-annotator agreement with F measure. So the basic conclusion here is that Krippendorf's alpha is a standard reliability statistic for inter-annotator agreement. That's the one that you should use. We're going to go through calculating all of the measures, but the one that you'll use in practice is Krippendorf's alpha. It is unfortunately not widely available in most of the statistical software packages, and it can be a little bit more difficult to calculate, which you're going to find out as you go through it. And that's what I think limits its use and availability. People are going to use easier measures, not because they're better, but because they're easier. And so I think that's just something for you to consider. There's certainly nothing wrong with using a Fleiss Kappa. There's a project that I did dealing with organ transplant. And we were looking at the decisions when a deceased donor organ is offered to a surgeon or transplant center for transplantation into a patient on the wait list. That transplant center or surgeon has to make a decision to either accept or reject the offer. And so we can measure in mock offers the level of agreement between medical decision makers. And in that case, I chose to use Fleiss Kappa because it allows me to measure the inter-annotator agreement between medical decision making, but there's an explainability trade-off, right? Where I felt that because I can explain Fleiss Kappa with greater clarity and ease, right? That this metric here of the probability of mean agreement and the probability of expected agreement is a lot easier to explain to medical practitioners who probably don't have the same level of mathematical and statistical rigor as a computer scientist. It allows me to explain the concept better than Krippendorf's alpha, which is, I think you would agree, even as a computer scientist, that's a much more complicated equation and takes a lot more to gain acceptance. So from an explainability perspective, I chose to use Fleiss Kappa over Krippendorf's alpha. And that's another consideration you have. So it's important to kind of have a good overview of the different measures that are used, so you have literacy when you're looking at papers or literature, that you can actually think about other considerations from explainability, transparency when you're selecting a measure versus straight performance, which would definitely be Krippendorf's alpha. Hope you have enjoyed this lecture, and I hope this has been interesting. The other note that I want to caveat, and this is important, is you can read a lot more detailed explanations of each of these measures on Wikipedia. And the reason why I mention that is the Wikipedia will give you examples of calculations on this, will give you detailed explanations, and that is a resource that you will always have. You're not dependent upon my lecture. Oh, where did Ian McCullough put this, that, or the other thing? Did I save his lecture? If I'm looking at the slides, do I remember what he said? I'd rather equip you with a resource that will be there that's more enduring for you to be able to reference, because you're going to go through this and you're going to learn how to calculate these measures by hand, which will give you a deeper understanding of the measure, but you're going to forget those details several months after the class. It will have equipped you to be able to better acquire the knowledge again in the future. It will help you get you a better understanding of the trade-offs of different measures, so that's why we do it. But as far as a utility, I'd rather just equip you with a resource that's going to be there long after the course. And so that's why I'm going to leave a lot of the details of how you actually go through and conduct these examples to the examples that are on Wikipedia. So again, I hope you've enjoyed this lecture, and I hope you have appreciated the importance of this topic on machine learning in general.